In this lecture, we'll have a look at some results for the OLS trend line. So the setup, we have some X data and some Y data. In this example, X is the number of hours that students study for a course, and Y is the result on the final exam. I have fitted a linear trend line, and these are the OLS slope and the OLS intercept. Based on the trend line, I can find fitted values and residuals. Fitted values, remember, are just equal to B1 plus B2 times Xi, and residuals are equal to Yi minus fitted Yi. So let's go back. So here's the first result. Well, soon at least, just stating again here that B1 and B2 are now the OLS values of slope and intercept. So it's the OLS trend line. And EI, YI hat are the residuals and the fitted values. So now we have the first result. The first important result is the following. The sum of the OLS residuals will always be equal to 0. Not approximately 0, but exactly 0. We can check that this is actually the case. If I just do here, sum of all the residuals, it will come out to be precisely 0. Some observations are above the trend line, some observations are below the trend line. If you sum all these residuals, you will end up with 0. So it doesn't make any difference how I change my data, no matter what I do here. If I change my data somehow, say I change this to 77, that will definitely change my OLS estimates B1 and B2, like this. It will change the fitted values and the residuals, but they will still sum to 0, no matter what you do, and no matter how you change your data. It's not hard to realize and prove this. It's a result that follows from one of the normal equations. Remember, the normal equations are the first order conditions for minimizing RSS. And one of them, the first normal equation, let's write it as the normal equation 1. Well, that was the following: summation yi minus b1 minus b2 xi should be 0. This sum here, with the exception of a minus 2, is the partial derivative of RSS with respect to b1, and that derivative needs to be 0. Well, if you look at this parenthesis here, you can see that this is exactly the definition of the residual. So the normal equation 1 can just as well be written: the sum of all the residuals is equal to 0. Well, if the sum of all the residuals is equal to 0, then the average of all the residual must be 0. So the average of the residual is 0. Simply because the average is the sum divided by n, and if the sum is 0, you have 0 divided by n, which is 0. But we actually have more important results from the linear trend line. The next one is the following. If you sum the product of the x variable with the residual, you will get 0 as well. First, let's check it. So if I do x times, let's actually insert a new column. If I do x times e here, so I do my x variable, I multiply that by my residual, like that. I copy this down here, and then I sum all of these. then this sum will also be exactly equal to 0. And again, it doesn't make any difference how you change the data. Change maybe this one, for example, to 100 and whatever, 46. Again, B1, B2 will change, all the fitted values will change, all the residuals will change, but these two sums will remain 0. So Control Z. How do we prove this? Well, if you're thinking that didn't we have two normal equations, and perhaps it's the second one, you will be completely right. So normal equation 2, that was this one, xi and again the parenthesis is simply ei. So what it says is that xi times ei, that must sum to 0. This result has a further consequence, and that is the following. The sample covariance between the x data and the residuals will be 0. Let's check that this is the case. So let's find the sample covariance between x and e. Remember, the sample covariance tells us whether they covary positively or negatively or not at all. And it turns out that they do not covary at all. So we do covariance.s, put the x data, put the residuals, and parentheses, and we get a sample covariance which is 0. Now if you haven't formatted these cells as numbers with a fixed number of decimals, the cells that are supposed to be 0 may actually turn out to be not exactly 0 due to rounding errors. So it could be something like a number times 10 to the minus 16, for example. So 16 zeros and then some numbers. But that's just a rounding problem, because Excel can't calculate numbers exactly. So let's see if we can prove this then, that the sample covariance is 0. So remember that the sample covariance between x and e is given by 1 over n minus 1 summation xi minus x bar ei minus e bar. That's the formula for the sample covariance between x and e. We know from normal equation 1 that this is 0. Xi minus x bar times ei. And if I open the parentheses, this is 1 n minus 1 summation xi times ei minus x bar times ei. I can divide this up into two sums. Summation xi times ei minus summation x bar times ei. So we know that this is 0 because of normal equation number 2. For this expression, we can just take that as a constant now. So we can take it outside. So it says x bar summation ei. But we know that that's 0 because of normal equation 1. So it's 1 over n minus 1, 0 minus 0, which is 0. Alright, if the sample covariance is 0, then the sample correlation will be 0 as well. Because the sample correlation is simply the sample covariance divided by the sample standard deviations. So it's 0 divided by something. So the sample correlation will also be 0. So we have OLS results slide 2. The sample correlation between the explanatory variable and the residuals must be 0. Moving on, we actually have more results. The next one is the following. If you sum all the fitted values and you sum all the y values, you will get the same result. So let's go ahead and check that. If I sum all the y values, I will get some of these. I get 651. And if I sum all the y fitted values, well, actually what you can do is you can just copy the formula over like that, because it will then change the C reference to the D reference. So you can see now it's done sum D2 to D10. And you can also see that they do have the same sum. How can we show that they have the same sum? So why is it true that summation of the actual y values is equal to the summation of the fitted values? Well, we know that the residuals are defined as the difference between these two. And we know that the residuals will sum to 0, so we can probably use this. If I move this over here and this over here, we have yi hat is equal to yi minus ei. So if I use that here, we can see that the summation of fitted values is the same thing as summing yi minus its residuals, and that I can divide up into two sums. And I know that this is 0, so this comes out to be the same as summing the y values. Again, it makes no difference what the data looks like. No matter what the y values are, this will always be the case. We then have the obvious extension of this. If I divide both sides by n, then I get the average of the fitted values on the left hand side, and I get the average of the y values on the right hand side, and those must be equal as well. So this must be true. This weird notation with yi first with the hat and then with the bar simply means the sample mean of the fitted values. The sample mean of the fitted values is the same as the sample mean of y. Where I just fixed a typo. There should be no subscript on the one to the left. Alright, we actually have more. The next result that we have is the following. If you sum the product of fitted values and residuals, you will get 0 as well. Let's check first of all that this is true. So let's do a y hat times e here, multiplying fitted values with residuals. Copy this down, sum it, sum these, and we get 0. So let's try to understand why this is 0. Summation yi hat times ei. So we know that yi hat is b1 plus b2 xi. We can use that and replace yi hat with this. So then this sum is sum b1 plus b2 xi times ei. Open the parenthesis, it's sum b1 ei plus b2 xi ei. Write this as two sums, sum b1 ei plus sum b2 xi ei, and take this outside, knowing that the sum of ei that's left is 0. We get b1 times 0. Take that outside, remembering that the sum of xi ei is 0, we get b2 times 0, and that's 0. This result can then be extended to the sample covariance and the sample correlation. So this means that the sample covariance between fitted y and residuals is 0. So if I just do covariance.s, I do my fitted values and I do my residuals, then we see that that is also 0. Why? Well, because pretty much the same idea as when we show the sample covariance between x and e is 0. The sample covariance between fitted values and residuals is 1n minus 1 summation yi hat minus yi hat bar ei minus ei. Well, should not be a I here or here. That's the definition of the sample covariance between fitted values and residuals. Well, this is 0, as we've seen before. So this is 1 n minus 1 summation, and this is the same thing as y bar. So summation yi hat minus y bar ei, which is 1 over n minus 1 summation yi hat ei minus summation y bar ei. This we just saw that that's 0. This one, take this outside, and summation ei is 0. So this is 0. And if the sample covariance between fitted values and residuals is 0, then so will the sample correlation between fitted values and residuals will be 0 as well. So just a few things to emphasize here. First of all these results hold no matter what the data looks like. But the key point here is that the B1 and B2 that we use are the OLS values, with an intercept. If I change these ones, if I don't use the OLS trend line, then none of the results that we have talked about will hold. Specifically, if you fit a trend line with no intercept, if you have no intercept, then none of these results will hold. So it's only for the OLS formula with intercept. So, final point, these results do not hold if the trend line has no intercept.